Hello. We've seen previously that in quantum mechanics we describe particles in terms of a quantity called the wave function, denoted with the Greek letter psi, which tells us something about the probability of finding the particle. But it can't tell us exactly the probability because psi is in general a complex number. Additionally, it has what's called a global phase. So it has some complex phase out the front which is gauge dependent, meaning that it's a mathematical choice as to what value that phase takes. It's a mathematical redundancy in the system. So psi itself can't tell us about probabilities. In fact, psi denotes what's called a probability amplitude, which we usually just refer to as the amplitude. To identify the probability itself, we need to use what's called the Born rule, which tells us the following. The modulus square of psi multiplied by a small line element dx in one dimension gives the probability to find the particle between x and x plus dx at time t. In general, this will be a small volume element in 3 dimensions. So it's this quantity that we need to be looking at for probabilities, and this has all the properties we'd like. It's a real number. It no longer has this arbitrary global phase out of the front. And in fact, if we integrate the modulus square of psi across all of space, we'll get the value 1, because even though we don't know where the particle is, we know that it must exist somewhere. In fact, we can identify this quantity here as what's called the probability density. And it's this which, integrated over a region of space, gives the probability to find the particle within that region. Since integrating it across all of space gives the value 1, we actually have what's called the global conservation of probability. The probability of finding the particle is always a constant. In fact, there's a stronger condition on the probability, which we'll take a look at now with a worked example. Let me just move over to my worked example area. Okay, so we have the global conservation of probability, but to get a stronger constraint on it, let's take a look at our probability density, and let's look at the time derivative of it. So it's a little bit bigger. Our probability density is defined as modulus psi squared, which is equal to psi star psi. Well, I've omitted the position and time dependence, but they're there. And so what we'd like is the time derivative of this, the partial derivative of the probability density with respect to time, holding position constant. And so this, of course, will be equal to psi star dot psi plus psi star psi dot, just from the chain rule. And then to work out what these quantities are, we can use the time-dependent Schrödinger equation, which tells us that, myself a bit of space here, I h bar psi dot equals, I'll write the Hamiltonian out in full, minus h bar squared over 2m rad squared psi plus b psi. And so dividing by h bar and multiplying by minus I, we have psi dot equals minus I over h bar minus h bar squared over 2m rad squared psi plus b psi. How about psi dot star, psi star dot? We just take the complex conjugate of this, and so we get psi star dot is equal to I over h bar minus h bar squared over 2m rad squared psi star plus b psi star, where the potential is assumed real. Okay, so substituting both of these back into this expression up here, we find that we have rho dot is equal to, so we get the I over h bar out the front, minus h bar squared over 2m rad squared psi star plus b psi star, and all of this is psi star dot, this gets multiplied by psi, plus, it would be plus psi star times psi dot, psi dot, but remember that there was a minus sign in front of the psi dot compared to the psi star dot. So actually this should have been a minus, and then otherwise inside it's pretty much the same thing with psi instead of psi star. Okay, so here we have v psi star psi, and here we have minus v psi star v psi, and so these are the same thing. And bringing the, so what's left, we have minus h bar squared over 2m out the front of both expressions, and we can bring that out the front to get rho dot is equal to minus I h bar over 2m. Let's bring the psi, the left of grad squared psi star, because the grad squared only acts on the psi star. It's inside these parentheses. But psi grad squared psi star minus psi star grad squared psi. Okay, to go a bit further, we need to use an identity from vector calculus. I'm just going to fold this paper over just so we see it a bit more closely. So we know that, and you can just you can drive this yourself or look it up, but we have, and I'm going to look it up off my bit of paper. So if we have f grad squared g, we can always write this as the divergence of f grad g minus grad f dot grad g. So taking a look again at our previous expression here, in the first term f is psi and g is psi star, and in the second term those two switch, and so we end up with the result that rho dot equals minus I h bar over 2m divergence of psi grad psi star minus grad psi dot grad psi star minus the divergence of, and switch all psis and psi stars, like so. And we see that this term is the same as this term, so these cancel. And the rest of the terms that remain have a divergence term on the outside. And so we can say that rho dot is equal to minus the divergence of some quantity we call j, where j, which is in general a function of position and time, is equal to, we've taken the minus out the front, so we have I h bar over 2m psi grad psi star minus psi star grad psi. And it's a vector quantity in 3 dimensions because of the grad here. So this is our stronger constraint. It tells us that not only is probability conserved globally, but it's actually conserved locally. And what this means is that this expression here is an expression for a general fluid, which is what's called a continuity equation. And it tells us that, imagine we have some little box in space, which originally had some probability density, but this goes down, it changes in time. Well, it would be consistent with global conservation of probability to have another little box separated off in space somewhere else, have the probability go up just instantaneously. That would be compatible with global conservation of probability. But what the continuity equation tells us is that actually it's locally conserved, and so there must be a flow of probability density between these 2 points. If the probability density is to go down in one region, there must be a divergence of this current out of that region. There must be some flow out of this region into that region. And so for it to go down from this box and up in this box, there must be a flow between the two boxes. And this flow is a flow of this quantity J, which is called the probability current density. There we go, probability current density. So let's take a look at some general boundary conditions that we can apply on psi as a result of these ideas. Let's take a look at some boundary conditions then. The first boundary condition on the wave function is that it has to be continuous across space. And the second condition is that the first derivative of psi with respect to x is also continuous. In fact, the second condition doesn't hold in all cases, but there are fairly pathological cases where it doesn't hold. In fact, psi prime, the first derivative with respect to position, is continuous provided that there's no infinite discontinuity in the potential. At places where there's infinite discontinuities, this may not hold. So let's add that caveat. So these boundary conditions really come from the fact that we don't consider potentials which are too pathological. In fact, we can consider jumps in our potential. We can even have delta function potentials, but we don't consider anything worse than that. A final condition, which is not really a boundary condition, but which generally applies, is that in regions where the potential is infinite, we require the wave function to go to 0. The reason for this is that the modulus square of the wave function is the probability density, and we require the probability density to be 0 in regions where the potential is infinity in order to keep the energy finite, which is something we'd like to do. Okay, so let's take a look at some of the philosophical ideas behind the interpretation of these objects. Dirac, in his textbook, gives a very good explanation as to why we might expect probabilities to come up in quantum mechanics. We'd like descriptions of things such as light, which are familiar on the macroscopic scale, but descriptions which work down on the microscopic. When we see a beam of light, like the spot from this laser pen, and it works, we can of course describe this classically, and we can use Maxwell's equations to describe it. But we'd like a quantum description. So Dirac gives us the example of taking a crystal, something like calcite, which I have here. So calcite is birefringent, which means if I shine the laser through the calcite, my one spot should turn into two, you can see there. And as I rotate the crystal, actually one spot will rotate around the other, and these two spots have different polarizations. The key thing is just that there's two spots now. So why is this a problem? Well, it's not a problem on the classical scale, because we just say, well, there's a beam of light, it has some amplitude and some intensity, and the intensity just splits into those two beams. But if we're going to come up with any kind of description of this on the scale of single particles, it's going to have to somehow account for each particle either going one way or the other. So there's got to be some kind of probabilistic element to it. The same idea leads to problems in the idea of the atom. So we already had a problem after the Rutherford experiment showed that atoms have a positive nucleus with negative electric charge around it. Why doesn't the negative charge drop into the positive and minimize its energy? When Schrödinger wrote down his description of the atom, according to the Schrödinger equation, he initially had the idea that the probability current density that we've just identified may be described the current density of the electron as it orbits the nucleus. But then that gives us a problem again, because if the electron is really orbiting the nucleus, then it's moving in a circle, and an electric charge moving in a circle radiates energy, and so it should lose its energy and drop into the nucleus again. So according to Feynman in the Feynman lectures, Schrödinger originally interpreted the probability current density as a literal current density of the electron. The idea was that when we go down to the quantum scale and we look at individual particles, such as photons in this case, each photon will be kind of spread out in exactly the same way that the intensity of the light is spread out. But that can't be true because when we observe the particles, we always observe them at a single location. It also can't be true because if we think about the electron trying to orbit the nucleus, it would be losing energy. This is where Born came along with the Born rule and why the Born rule is so important. He told us that the current density was not the current density of a smeared out electron. It's the current density of a flow of probability. But when you look for the electron, you always find it in one specific place. So the electron is not spread out. Quantum particles aren't spread out. Their probabilities are spread out according to their amplitudes described by the wave function. And Born told us that the modulus square of that amplitude gives us the probability for finding the particle in a little region. Okay, thanks for your time.